Hello everyone. This is my English speaking practice and I'm working on coding problems. Today's problem is H-index 2. Let's get started. Given an array of integers citations where citation I is the number of citations a researcher received for their ith paper and citations is sorted in non-descending order, return the researcher's H-index. According to the definition of H-index on Wikipedia, the H-index is defined as the maximum value of H such that the given researcher has published at least H papers that have been cited at least H times. You must write an algorithm that runs in logarithmic time. So, let's take a look at example 1. Input is citations like 01356 and the answer is 3 because 01356 means the researcher has 5 papers in total and each of them have received 01356 and 6 citations respectively. Since the researcher has 3 papers with at least 3 citations each and the remaining 2 with at least 3 citations each and the remaining 2 with no more than 3 citations each, their H-index is 3. Yep. Yeah, I solved this problem, but I forgot. What is the difference? The H-index 1 and 2. In this solution, I implemented the binary search. So yeah, the basic idea is explore the threshold, and which is the number of citations, right? And I implemented is okay function, and if it's okay, we can update the answer, right? Because because we have to return the number of papers, so threshold. Oh, is this correct? I'm wondering, the threshold might go up or go down, so why I update answer? Why do I always update the answer? If the threshold is okay, yeah, okay, I see. If the threshold is not okay, we update the right pointer, and so it means the ranges we explore are going down, so we cannot update the answer in larger value, in larger direction. So when the threshold is good, we can update the answer, and it should be greater than the current answer value. so we always update the answer if it's okay. And yeah, let's take a look at this function. This function takes threshold, and yeah, in this function we also do the binary search, and because we need to check if the threshold is less or equal to number of cited papers. What is it? Number of cited paper. Number of cited paper. Yeah. So we want to find out the index. Yeah, the citation is sorted in ascending order, and here we want to find out the index. It point to the number of citations, and yeah, that is called target, and target should be greater than threshold. So in other words, the index point to the minimum value, how to say, 式値より大きい、なんていうかな、式値より大きい、まあローワーバウンド、式値より最小の値を求める。Find the smallest value that is greater than threshold. Find the minimum value greater than the threshold. Yeah. Lower bound. Is it called lower bound? Almost, but there is an important distinction. It's commonly described using a lower bound, but the value you are asking for is not the lower bound itself. Precise terminology. Suppose you have a set S and threshold T. I want the smallest value in S that is greater than T. Formally like this, and how the lower bound fits in is lower bound is upper bound and lower bound. In this case, it's included. So lower bound the smallest value greater than threshold. maximum value. That is the SOI equal to X. Example, if the set is 100 and 200, then even though 3 is not the lower bound of this. Okay, I will go with this definition. So when we get the threshold t, the first element that is greater or equal to t is the lower bound of the set. So this case, I have threshold and I also have citations, and I want to find out the target, which is the lower bound of the citations. Lower bound with t of the, in the citations, right? So the index is the lower bound, right? Lower bound. Yeah. Index is the lower bound, and when we after we can identify the index. We calculate n minus index, which is the number of cited papers, which is cited at least threshold times. So if this value is greater or equal to threshold, the threshold is good. This can be H in H index, right? So that's the algorithm here, and this algorithm is already implemented like logarithmic time, right? So so we can implement it in the same way, right? So I'm gonna code it and explain it. Okay, let's see the constraints. So let me think. I often get in trouble when implementing the binary search, because the indices are getting complicated. I always confused So let's implement the skeleton. We have left and right pointer in order to implement binary search, and the range is initialized with 0 and this could be threshold. So yeah, it should be 1001. All right, and yes, and answer is -1, while while the difference is more equal to 0, we can continue it. Threshold is decided by like this: right plus left divided by 2. This is the threshold, and if it's okay, and we can update the threshold, and which can be the answer, right? Yeah, because the value is valid as a h. So let me see the definition of the h. The h index is defined as the maximum value of h such that the given researcher has published at least h papers that have each been cited at least h times. So yeah, this is the h, and this can be the answer. And if it is okay, there could be a possibility to increase the threshold, right? Because we don't explore all possibility yet. So in order to check further possibility, we update the left pointer, because we need to sift the range of exploration to a larger side. So the left is t plus 1, and otherwise we found the t is not enough, not sufficient, which is correct, and t is not valid. T is too large, right? T is too large. So we needed to shift the range of exploration to the smaller side. So we move the right pointer to t minus 1, right? Because we already checked the t, so we don't need to check the t again, So t plus 1 and t minus 1. Yeah, this makes sense to me. And we can return answer directly, because after breaking this while loop, we will have finished exploring all possibilities, and the answer should be updated, and which is the optimal value. Yeah, which is a kind of lower bound. In this case, the set is this 0 to 1001. Yeah, this is the set, and the lower bound means the in this context, there is no threshold, but there is no specific value as a threshold, but this condition is the kind of threshold. So the answer is the lower bound, and in other words, the answer is the smallest value that meets the condition that meets this condition, right? Yeah. Let me say it again, that the answer is this lower bound, and in this context, the answer is the smallest value which meets this condition, right? And then we are going to this condition is okay, right? Threshold. Threshold. So this condition is representing this part, and each index is defined as the maximum value of h, such that the given researcher has published at least h papers that have been each cited at least h times. And so the citations is sorted in ascending order, so as you can see like this. And if the threshold is 3, we need to find the lower bound with the threshold 3, right? So should be point here, right? Because if we can find out this point, we can find out how many papers that have been cited at least 3 times, right? So if the threshold is 2, we also need to point to here, right? This is also lower bound, because 1 is not enough. The 3 is the smallest value. Yeah. So yeah. Okay. So yeah, what we are going to implement is to get the index of the lower bound with threshold, right? And then we can find out how many papers that meets condition, and the number of papers that meets condition should be greater than threshold as well, right? Because at least H papers that have been have each been cited at least H times. Yeah, that little bit complicated, but yeah, that is the condition. So we implement the condition here. This is also implement it like left and right pointer, right? And this time the range is 0 and the n is length of citations, right? While the difference should be positive, and the index is -1. Yeah, at first, and the middle so the middle is the target. Middle is the target, and how to find might be duplicated. Might be duplicated. Yeah, the citation value might be duplicated. So if the target meets condition, we can update the index like this, and we can we want to go down because we want to find the smaller index. So the right pointer should be like this, and otherwise we need to update the left pointer because the middle, the target is less than the threshold, right? Yeah, we want to move toward right side. Yeah, and break it. So basically we can find some target, and the index should be updated like this, and we can find out the number of cited papers, cited papers, right? Number of cited papers is like n minus 0, 1, 2, So index, right? Yeah, but there is one exception. Edge cases, we cannot find any index, any valid index. So if not index, it's -1, and otherwise it means the index still remains -1. That is, we cannot find any valid index. So the threshold is too high, so number of cited papers is 0, of course, and return the condition. So number of cited papers. So papers should have been cited at least threshold times. Let's see the results. Index out of range. Middle. Oh, really? Left plus right. What happened? What? I always have trouble in indices. 0 and 5. So the middle is 2. Middle is 2. 2. 0, 1, 2, 3, 4, 5. So 5 is not good. But right is 5, 5, 5, 4, 5, 4. Okay. n-1,000. Okay. Great. So I've already solved it, right? Okay. So today, instead of moving on to the next problem, I want to introduce my blog, and I've learned about memory management in Linux system, and I published some articles. But how do I practice my English? How do I practice speaking my English with this? Memory management. Or okay, let's take a look at this article, because I'm going to forget the contents about this page, so in order to remember it, I'm going to read through this article. Yeah. What is IRQ? Introduction. Have you seen IRQ in Borrow messages? I'm going to understand what it is. Yeah. Asynchronous interrupt. IRQ stands for interrupt request. It's a signal from hardware devices of the kernel. On the other hand, there are synchronous interrupts, which are the opposite of asynchronous interrupts. In synchronous interrupts, software triggers the interruption. I think the processor keeps executing the same thread even when software triggers it. That's why this is called synchronous. In other words, an asynchronous interrupt is sent to a processor that is executing a different processor or thread. For example, when a process initiates disk I/O and waits for its completion, a context switch occurs and the processor executes another process. When the disk I/O completes, the IRQ is triggered. Okay? And the kernel has interrupt handlers. There are two types, top half and bottom half. The top half is a handler that initially receives interrupts. This handler is designed to pass tasks to another handler because it cannot access interrupts while processing them. The handler that takes over these tasks are called bottom halves, right? So there are two types of handler, and the top half just receive the interruption and immediately take it over. Pass it to the bottom half. And bottom half mainly handle the tasks. And the following are examples of asynchronous interrupts: timer, data reception by network interface card, and write completion to disk, input from keyboard or mouse, USB connection. And example about data reception by network interface card. The top half notifies the hardware and copies data to memory to free the hardware buffer. Top half notifies the hardware. The bottom half processes TCP and IP. Yes, I think the memory means the area for memory mapped IO, and the DMA. Mm. So this is at the level of the data link, logical connect level, logical connect layer, I think. And I don't make sense about this. The top half is notified from the hardware, I think. The corner, yeah. So in my understanding, uh hmm I will Google it later. But yeah, the important thing is that the handler is separated into top half and bottom half, and the top half plays responsible for data link layer, and it copies data to the memory, and where is used for memory mapped IO, and which is in the kernel, kernel space, I think. Yeah. And after that, the tasks are passed to the bottom half, and the bottom half process need to read the data from that area, right? Yeah, and which is but bottom half is also in the kernel, right? Interrupt handlers. Yeah. I'm not sure, but I'm in my understanding that kernel receives the data, and then the user process reads the data from that area, right? Which is included in TCP/IP protocol. I understand that there are two main types of bottom half. One is soft IRQ, and the other is WACQ. WACQ was developed later and previous more. Okay, I almost forget it. How to view statistics? Interrupt statistics you can see with this command cat proc interrupts, and it's like this. There are two CPUs, and okay, let's see the format. IRQ number and CPU and interruption controller, trigger mode and devices. And the column description. IRQ number is IRQ number. Okay. CPU column, cumulative count of interrupts handled by each CPU core interrupt handler hardware such as IO, APIC, or PCI, MCI. MSI that manages interrupts. Actually, I don't know about these handlers for now. Trigger mode as well. Device. Okay. Let's see example explanation. 25 is like this. NVMe storage handles 25,975 times by CPU 0 and 0 times of CPU 1. Interrupt from NVMe SSD Q1. Right. Biased towards CPU 0 due to affinity settings. And 28 0 26,672 PCI MSI, and this is the name of controller, and this is the name of device. The transmit and receive Q0 of network interface, which is ether 0, and primarily handled by CPU 1. Special interrupts. LOC, local timer interrupt. Rescheduling. Function calls between CPUs. TLB shutdowns. Okay. So TLB is here. Okay, there are special name of interrupts. From this information, we can see which CPU handles which interrupt and the load balancing situation. Exactly. So some interrupts are biased towards a specific CPU core, right? And software IRQ statistics, you can see this command cat proc software IRQ. So software IRQ is the software interruption, right? Software interruption, okay, which is called synchronous interruption. Okay, is one of the bottom half mechanisms. Oh, I see. That takes over processing from the top half that handles hardware interrupts. Each row shows the number of interrupts executed by CPU grouped by software IRQ type. So in this case, net received CPU 0 and CPU 1 processed a lot of interrupts, but CPU 0 has more interrupts, indicating that network interrupts are biased towards CPU 0. Performance analysis uses when NetIRX is biased towards specific CPUs, IRQ affinity adjustment may be needed. When timer or scheduled values are high, it indicates high system overload. It means there are a lot of context switch, I think. We can trace the flow from hardware interrupts to software IRQ by viewing with we can combine it. Okay. It's like 62, 63 thousands. It doesn't match. Maybe the time is different. And demo code. The following demo code demonstrates using tasklet as a bottom half. It uses a timer to trigger interrupts. The timer handler acts as the top half and delegates processing by a tasklet schedule. The tasklet handler is a function that emulates heavy processing. In my experiments, I confirmed the top half completes in processing in about 200 nanoseconds on average. Let's see. So, what is it? Tasklet handler, timer handler, tasklet demo init, tasklet is, this is one of the kernel module, and tasklet setup, timer setup, mode timer, tasklet demo init is loaded here. Tasklet demo is here. Tasklet setup, timer setup, and what I demonstrate. Timer handler acts as a top half and delegates processing by a tasklet schedule. Let's see, timer handler. I think here. So this is used here, and this function behaves as the toplet handler. Yeah. But I should have written the output of this code of this demo. Yeah. So timer handler is registered here, timer setup. So I think this is the top handler, and top half start and top half end. So between this function, just call the tasklet schedule, right? So I think this is so short. This is so short. It just call tasklet schedule, right? So it's not executing this function. Tasklet is like this, and the handler is here. So the tasklet schedule my tasklet means tasklet handler is appended to the task queue, and it have 5 seconds delay, which emulates the heavy processing. But for this function execute it immediately, because it's not executing this function. It just pass the tasks to the tasklet, right? Which is what I wanted to show in this demo. Okay, and at last, from a performance perspective, according to interrupts and IRQ tuning, each IRQ have a property called SMP affinity, which defines a CPU core that can execute the interrupt service request that IRQ. Application performance can be improved when configured properly. By assigning the same CPU core for both interrupt processing and application threads, you can achieve ability to share CPU cache lines, reduction of memory access latency, reduction of context switch overhead. You can view or modify the IRQ affinity in the proc IRQ number SMP affinity file. The value are represented as hexadecimal bit mask, where each bit corresponds to a CPU core. So example, configuring only CPU 0 to process Ether 0 IRQ32 on a 4-core system. At first, you can confirm the current settings. So we use cat command and F. F means this is a bit mask, so hexadecimal bit mask. So 1111, right? Hexadecimal bit mask have F has F is 16, right? So 1111, yeah, it have 4 bits. And yeah, so this is a 4-core system, so each bit corresponds to each CPU, and F means all 1 bit, right? And set it to only CPU 0 equal 1 to SMP affinity, and you can see F is changed to 1. It means the CPU 0 and just only the CPU 0 to process the interruption of 32, right? Okay, closing thoughts. In this article, I learned about the familiar term IRQ. I learned that properly configuring IRQ affinity can provide performance benefits. However, from a network performance perspective, IRQ affinity configuration is not always optimal because of mechanisms like receive side scaling (RSS), which improves network packet reception by distributing packets across multi-cores. Additionally, new topology should be considered when configuring affinity settings. Yeah. Receive side scaling, which distribute packets across multiple cores. So if you set the affinity like this, this is my guess. Yeah. I think the distributing packets across multiple cores more efficient because um, they can handle the packets at the same time. So I'm not sure which is efficient. Yeah. Mm. But I understand by assigning the CPU's core for both interrupt processing and application threads, we can achieve the ability to share CPU cache lines and deduction of memory across latency. Mm. Mm. So I need to learn more about it. Thank you for watching. Bye.